Okay, so here we are continuing with our timer 1 PWM outputs on PB1 and PB2. We verified our timing on our period for our cycle was exactly 20,000 microseconds. But what we need to do is something to update the output values for the OCR1A and OCR1B registers so that we can see the pulse width changing and simulate it. Now, I mentioned earlier that I was going to use the analog to digital converter with a potentiometer. However, that's difficult to simulate in AVR Studio to simulate an analog input. When we get to that point, we can manually put values in the analog ADC register, high and low byte, to simulate reading a value. But for now, I have data, a table of data that I used on a pair of videos on YouTube called indirect addressing. So we can use the same table of data that will make the servo motor sweep in a sinusoidal motion, so it will accelerate across the middle of its travel, then decelerate when it gets to either end of the travel and change directions, and then accelerate across the middle of the travel again. So I have created some interactive Python notebooks, and I have the code in there with tables of data that we can copy and paste into our memory, and then we can write a function that will read the memory, the data values from the memory, and update them in the OCR1A and OCR1B register values. So for now, we'll just do the OCR1A timer. Maybe later we can combine it with an OCR1B value. But first, let's go look at the data. And what I did is I created some web pages on GitHub. And so I'll open that page here. So notice the address so that you can go to the address. It's harrimand.github.io. And then these are different tables of different lengths so that they cause either 1 second, 1.5, 2, 3, or 4 second sweep time. And you can copy one or more of those tables to your program memory in your AVR. So I'm going to go ahead and do the 4 second sweep. That's the largest table. And this is the Python code. But mostly we're interested in, well, this is the sinusoidal waveform that we want to have. And then I've got the values that will be added, or sign values when you add the negative value, will be subtracting to the OCR1A or OCR1B register. So I wrote the code to generate the table of data here. So we'll just copy this entire table and paste it into our program. And then, if you're interested, you can see the other tables here too. But, so that I copied that table, and again, it's harrimand.github.io. So I'm going to go paste it into the end of our program here, and notice also that we have labels I copied at the beginning and the end of the table. So we'll use those labels to address our table and get the value. So if we're going to leave the program stored in program memory, then to read the value, we're going to have to use the LPM, load program memory instruction. The LPM instruction uses the Z address register for the high and low byte address for the location of the data to read in memory. And also remember that the LPM uses a byte address where the program memory is typically word addressed. So what I'm going to have to do is take the word address and shift it left by 1, and that effectively doubles a word address to make it a byte address, because there's twice as many bytes as there are words. A word is 2 bytes. So there's 2 bytes for each word. So we're going to have to load a Z address. For now, we'll load it with the beginning address of our table. So I'm going to do this up here, probably before we start the timer. And I could even do it up here. Okay. It doesn't matter much where we do it, but I want to do it before the timer starts so we can have everything ready to go when the timer is started. So I'm going to do it up here right after we configure the port B output pins. So I'm going to load the address of the table into the Z register. So LDI temp, and what the high byte of the address. And again, this is a word address, so table ADDR, and I have the number 4_0 indicating it's a 4-second sweep on this table. So it's going to take 4 seconds for the microcontroller to get from one end of the table to the other, if it's updating every 20 milliseconds, or reading a value every 20 milliseconds. But now this has to shift left once, because that word address, we need it to be a byte address. And then I'm going to, oh, you know what? We're doing this to the Z register. The Z register we can address directly. So I can do that to ZH, and then LDI ZL, the low byte of this same value. So that sets the address for Z to point to the first address in our table. Now we're going to have to also compare with a register when we get to the end of the table so that we know to reset the address back to the beginning. So we can use the either X or Y, we'll use Y I guess, as a compare register. So I'm going to load the Y register. In fact, you know what I'm going to do is copy these, save myself a little typing, and modify it. So we want to load the YH with the table end address. So we'll see we have the label at the end, table end. So we'll load YH with that. And that's the high and low byte. Okay, so that will allow us to do a compare with that register if our pointer to our memory is pointing to the address of the table end, which is one address beyond the end of the table, then we would need to reset that pointer back to the beginning of the table. And we're going to read that value and increment the pointer every time in the PWM update function. So what we're going to do here is a post increment LPM instruction. So we'll load the program memory, or load a value into temp, add it to the OCR1A low byte, and then we'll add with carry a 0 to the high byte, so that if there is a carry from the low byte addition, it will add a carry over to the high byte. So what we can do is set up a register, name it 0 if we want to, or we could just clear a register and add it to add to the high byte along with the carry byte. So again, we're going to do LPM, and the register, let's say temp Z plus. That'll load the value. Now we want to add that value to the OCR1A, which I called PWM AL. So we're going to add that value, ADD PWM AL, temp. And then we'll do it this way for now. Clear temp, and then add PWM AH, temp. So oh, this one's add with carry. ADC. So you want to add with carry 0, and then the carry bit, if there is a carry bit from the previous edition. So once we've added that, we're going to output that value to the OCR1AH. So STS OCR1AH, comma PWM AH. Remember, we have to do the high byte first, and then OCR1AL, comma PWM AL. Okay, so that will update when the timer overflows. It'll update that register. Now we need to see if our address on our table has reached the end of the table, and if it has, we need to reset it back to the beginning of the table. So we do a compare the low byte of our address with YL, because we set YL to point to the end of the table. So CP, and that's going to be ZL, comma YL, and then compare with carry the high byte, ZH, comma YH. And if we're at the end of the table, then those bits will be, those registers will be equal, and that will set the Z bit in the stack pointer. So if the Z bit is set, we want to reset the address back to the beginning. If the Z bit is not set, then we don't want to. So let's do a BRNE, branch if not equal to, and skip over instructions that will reset the address pointer. So I'm going to give it a name, no ADD, no address reset, right? And that's going to skip down here to a no address reset to the colon. Now here, what we're going to skip over is some instructions that will reset the address back to the beginning. So we can come back up here and copy our lines of code that we did that set the high and low address to the beginning of the table, which is right here, and paste them right here. Okay, so that sets the Z high and low byte back to the beginning of the table, and otherwise it will do, it will not reset it. And if we run this every 20 milliseconds, it should take about 4 seconds to get to the end of the table. So I'm going to assemble this and see how many errors we have. We have an error. I have an unexpected new line character, that \n. Really? Oh, notice here, I got an extra parenthesis in here. And on this one, because I did a copy paste, and I probably have the same thing down here too. I do. Okay, so let's try that again. Okay, that fixed our errors. Alright, so I'm going to run it, and okay, we got about a minute left on this video, a minute and 10 seconds, so we're almost done here. So I ran at full speed ahead to the breakpoint that was set. Now we're in the, here I want to verify that we're going to load the values and add them to register 15 and 14. So I'm going to step through quickly because we're almost out of time. You can pause the video and take your time and step through. But right now I notice that 15 and 14 have 001D in there. So I'm going to see what happens when we add the value. Z plus, so, oh, we already added the value at the beginning. Okay, let's try this again. I'm going to run full speed ahead and step here. And we're just about out of time. So go ahead and test that and see if it adds a value to the register, and then cycle it through to see the PWM update.